do I need to speak into a mic? Did you guys hear me? Yeah. So thanks very much for having me out. It's great to be here. I've heard about Merced before there was, Merced was here, I guess, but before there was a UC campus, because I was at UC San Diego and there was talk. So it's nice to see something here and to be here. And it looks like you've had a great speaker series, so it's really nice to be a part of that. And the capstone, no less. So yeah, I was thinking about experimental philosophy, sort of construed broadly, and experimental philosophy construed narrowly was something that I figured you would have heard a lot about, but I like to think about experimental philosophy more like empirical philosophy, where you're not constrained to just surveys, but more broadly to look at the way empirical science can inform philosophical thought. So I thought I would talk about animal models and the way in which, or the limits to which, we can extrapolate from understanding how other animals do things to apply it to our own kinds of questions about human cognition and human abilities. So this talk is also subtitled, Can Animal Experiments Illuminate Philosophical Problems? So what I plan to do today is just talk a little bit about empirical philosophy and its relationship to free will. And then I'm going to explain an experimental paradigm, the random dot motion task, and what we know about how monkeys do decision making. And I'm going to argue that we can extrapolate pretty directly from what monkeys do to what we do when we make decisions, and then consider a bunch of objections that suggest that, or that would be aimed at claiming we can't really use monkey data to make inferences about human decision making. And I won't say anything about freedom for most of the talk, and then at the very end I'm going to come back and think a little bit about whether the monkey data is illuminating at all to questions of free will. So as I was saying, I think of X5 as more empirical than experimental, or empirical philosophy rather than just surveys. And so there are a range of different techniques that you might use to illuminate problems about mind or questions about mind, and those can include things like Libet's EEG type studies. It can include functional MRI, and it can even include things like recording from single cells in tissue. One of the problems with recording from single cells in tissue is that you're pretty limited in what you can do in humans. There are actually people who are doing some single cell recordings in people who are undergoing brain surgery for various reasons. So there are situations in which you could do this kind of work, but in general it's pretty hard to get IRB approval for sticking electrodes into people's heads. And so I think that a lot of the insight that we might get from neuroscience about how human brains work is going to have to be indirect. We're going to have to use other kinds of model systems, since we can't really, just put electrodes into people because we're interested in how they make decisions. So could non-human animals tell us something about human decision making? And there's a history in philosophy that suggests that they can't. So famously, Descartes thought that animals didn't really have minds anyway. They were just like little machines, automatons lacking the soul. And Donald Davidson more recently argued that animals can't think. If anything without language can't think, so you might think that thinking is essential to decision making. That would rule non-human animals out. And some other philosophers who are much more naturalistically inclined might just think that the question of what's going on in brains is kind of irrelevant to the questions of, let's say, intentionality. So there's some tradition for thinking that we don't need to do any kind of translation between animal models and humans because there's no point. But I think that there's a much bigger push in the other direction to thinking that, in fact, because we're naturalists, because we understand the basis of evolution, there's good reason to think that we could learn a lot from looking at non-human animals. So just to show you the evolutionary tree. What I'm going to talk about is data from macaque monkeys, and make an argument that you can extrapolate from, or make an analogy between what's going on in those monkeys to what humans do. But those, humans and macaques diverged from each other approximately 20 million years ago. So there's still quite a bit of evolutionary time there. And, so it's quite possible, at least logically speaking, that humans are so different from macaques that nothing that we can learn from macaques is going to be of particular relevance to humans. But there is other evidence to go on aside from just evolutionary lineage. So we have quite a bit of data about homologies between the brains of humans and the brains of macaque monkeys. And in particular, the areas that I'm going to talk about, let's see, where are they? There. LIP, nope, back. Area LIP has, there are two areas, one in humans, one in monkeys, that are homologous, have similar cellular properties. So there's good reason, again, to think that what we learn about the behavior of cells in area LIP in the macaque is going to tell us something about the behavior of cells in the human brain. So that's just to sort of set the stage and argue that there are good reasons for thinking that we can learn something from looking at monkeys about human decision making. So now I'm going to tell you about a bunch of research that's been done in macaques in a perceptual decision task made under uncertainty. And so basically these tasks, these tasks were pioneered by Bill Newsom and Mike Shavlin, and I actually got to spend a summer working in Shavlin's lab and seeing the experiments close up and learning how they do the analysis and stuff. So this has been pretty revolutionary because it's provided us with a pretty systematic understanding of at least part of what's going on in decision making. So this is the, I'm going to show you the task that the monkeys do. Basically what the monkeys are given are visual stimuli, and they have to make a judgment about what direction of motion they're seeing. And in certain cases, the direction of motion is pretty evident. So the experimenter can titrate the strength of the motion signal in such a way that he can pretty much make the monkey as correct or incorrect on the task as he wants. Well, incorrect or random as he wants. So I'm going to show you what the monkey has to do, and basically I'll first show you a 5% coherent motion task. And so your job is to decide, are those dots moving mostly to the right or mostly to the left? So I'll stop that. And how many of you think the dots are moving to the right? And how many of you think the dots are moving to the left? Wow. You guys are good monkeys. And just to show you how differently the decision, or how easy or difficult the decision can be, if I show you the same task with a stronger motion signal, now it's pretty clear what direction the dots are moving. And so what the experimenter does is to show the monkey one of these little videos, and the monkey has to decide what direction the dots are moving. So here's basically what's going on in this task. So the monkey starts out fixating at a point, and then, and this RF here, I don't have a pointer, but that just denotes the part of the visual field that the cells that they're going to record from are sensitive to. And so the monkey fixates at the point, two targets come up that indicate direction of motion, then the monkey's going to keep his eyes at the center point. Then that stimulus is going to come on, and the monkey's going to have to decide which direction those dots are moving. And once he's made his decision, he moves his eyes to one or the other targets in order to indicate that he's made the decision and that's the direction that the targets go. And if the monkey's correct, he gets some juice. And if he's incorrect, he gets a timeout. So a little bit of a punishment for getting the wrong answer, because those monkeys are motivated to get their juice. So This is one version of the task, and basically what they measure is how correct the monkeys are, but also how long does it take for the monkey to make the decision. So if you notice those stimuli that I showed you at the beginning, the ones that have a very strong motion signal, you can decide pretty fast. The ones that have a weak motion signal, you kind of want to integrate evidence over time in order to figure out which direction of motion you're looking at. And so here's just a measure of the task performance. So you're looking at percent correct. As the motion strength goes up, the monkeys get better and better, and so they're pretty much always right when they have a very high motion strength signal. And similarly, the reaction time goes down, so they get faster and faster as the motion goes. And so this is a standard psychometric curve, and it turns out if you do the same experiment with humans, you get exactly the same kind of curve. So that's another piece of evidence that what we're doing and what they're doing in this task is very similar. So when you record from the monkey, so you can do you can record from different parts of the brain. If you record from area MT, which you see the recordings here, what you find, so area MT is a part of the visual brain that looks at or that analyzes motion. And cells in MT are going to be sensitive to motion in one direction or another direction. And what you see is if you measure neural signals in MT, the very strong coherent motion signal is going to give you high activity in those cells, and as the coherence goes down, so does the activity in the cells when you're recording from cells to which that are sensitive to that direction of motion. And so the MT cells basically signal whatever the level of motion that they're seeing in that direction at any given time point. But when you record from area LIP, you get a very different pattern. What you see is a ramping up of activity in LIP cells when those LIP cells are sensitive to the motion. So let me just preface this. LIP cells are actually sensitive to the saccade that the monkey makes. So when the monkey moves his eyes to one of the targets, if those cells are in that part of the visual space where the target is, when you're recording from cells whose receptive field is in the target area, and the motion is toward that target area, you see a ramp up, and the time it takes for the ramp to happen is proportional to the strength of the motion signal, and you see that there. But if the monkey's getting signals that go the other way, if the motion signal is moving in the other direction, and the monkey's not preparing to move his eyes to that part of the visual space, then you don't see that ramp. Okay, so essentially what those cells are doing is integrating evidence from the MT cells that are sensitive to motion in that direction. Any questions here? Yeah.
Sorry, they're ramping up at zero strength? So the signals at the motion strength signal is zero, and you still see a ramp up?
Yeah, so you see a ramp up, but it's actually sort of statistically, it depends which cells you're recording from. So you're going to get some signal, but essentially you're also going to get ramped down in another cell, right? So it's a random walk.
But is that indicative of their random saccades or anything like that? So
yes. So if you just look at 0% signal, this I'm gonna get to later in the talk. Good question. But what you see is there's correlation between just the randomness in the cells and the choice the monkey ultimately makes.
Oh.
So that's a great question. But there are two things that are worth noting. So one is that the ramp up, if you look at the time from saccade, so if you just sort of analyze everything with respect to the point at which the monkey's making a decision, those orange traces are the fastest ramp up, right? So they're making a decision very quickly, and the less strong the motion signal, the longer it takes for that ramp to go. So the slope of the line is less and less steep. But the other interesting thing is that everything ends up at the same threshold. Okay, so that suggests a certain picture of what's going on. And people have modeled this as a sort of drift diffusion model. So the idea is that there are some bounds that are set, and the information from the perceptual target gets integrated over time, and depending on how quickly that comes in, this signal is going to move towards one or another bound. So if you think about those bounds as defining various hypotheses that the monkey could have, in this case, motion is to the right and motion is to the left, then you can see that the evidence that he's getting from his perception is just gradually going to be integrated, and the stronger the evidence, the faster he's going to hit one bound or another. So this is a very powerful model, but also a pretty common model in psychology, not just for decision processes, but for all kinds of phenomena. And what I'm going to suggest is that this is actually a kind of a general framework for thinking of decision making, where there's no reason that you have to think of these various hypotheses the monkey can have as being specifically, tied to this perceptual signal, but rather you can generalize to any kind of hypothesis that the monkey could possibly represent. Okay. So this work focuses on area LIP, but I don't want to discount the fact that decision making is actually a much more complex process. There are a lot of brain networks involved in decision making beyond LIP. There's a lot going on with reward circuitry, and we know a lot already about dopaminergic neurons in the midbrain that contribute to the reward signal, and also their interactions with frontal cortex, which sort of at least seems to be assigning reward values to particular options. And then there are other kinds of areas of the brain that seem to be also involved in decision making. All of these have homologous areas in the human brain as well, but this is just to say that there's not, this is not the full story of decision making, but I'm going to suggest that whatever the full story is, it's largely going to be the same in humans and monkeys. So my main conjecture for the talk is that the monkey decision-making system is a good model for human decision-making. And what I think of as a sort of interesting philosophical problem is, well, to what extent can we support this or undercut this kind of conjecture? What reasons do we have for thinking it is not true? So I gave you some reasons for thinking that we can use this as a model. And now I'm going to consider objections to taking the data from the monkeys to be a model for human decision making. And I think that they fall into three main groups. One is that this is the wrong kind of task to look at for making, for understanding decision making. A second is that it's the wrong kind of content for it to be a decision making model. And the third is a larger objection that this is just like the wrong kind of model system for understanding decision making completely. So, all right, so objection one, that it's a wrong task. There are a couple different versions of this. So one version is that what we're looking at is a perceptual task and not a decision making task. That is, look, the monkey's just looking at the world, stuff is coming in from the world and it's doing all the work. The monkey's not making any decision whatsoever. So the first response to that is that if you actually look at philosophical discussions of free will, they tend to be exactly this kind of task. So, often you'll go to a first year, an intro philosophy seminar, and the way that the professor is going to illustrate it is going to say, if you want to raise your hand, and some people will raise their hand, some people won't raise their hand, and they say that's an instance of free will, right? Well, that's kind of the same kind of thing. There's no reason to decide yes or no. So it's not unlike the classic paradigms of free action. And there's no reason to think that free decisions can't be somewhat automatic. But more than that, as you saw from the original demonstration, that it's not just a simple decision task where the perceptual stuff is doing all the work, because in that 5% motion case, a lot of you really weren't sure what direction that the dots were moving, right? So as a decision under uncertainty, it's not just sort of a stimulus-driven kind of thing. You actually have to sit there and think, wait, what direction were those dots moving? So there's some kind of need for integrating evidence, but also deliberating about that evidence. Now, Now you might think that there's an issue here because, at least if we're thinking about most kind of decision making, we think we make decisions for reasons. So there's a difference between making a decision where you're paying attention to the reasons underlying that decision, or you're just picking one versus another option for no reason at all. So the classic example of that is you go into the cereal aisle and you see 70 boxes of Special K, and you don't sit there and deliberate about which box of Special K you're going to take. You just pull one off the shelf, right? And so if you care about things like moral responsibility, you might say, well, what we're really interested in is a choosing task, not a picking task, and that this is sort of like a picking task. I think that it's not, but I will come back to this and give you evidence for why I think it's not. But another reason to think that this might actually get at decision making is to look at this classic case of burdens asked. So this is another one of these sort of philosophical examples of what it is to make free decisions. And the idea is if the donkey is midway between either two identical things, or in this version, two things that he wants equally, the question is the donkey going to starve to death because there's no overriding signal? And some philosophers had suggested that you need free will in order to break this stalemate, right? So the donkey might starve to death, but a human wouldn't, because a human has free will and he would choose one or the other. But this 0% motion case is exactly that kind of case, right? Where there's a signal for choosing rightward, there's an equally opposed signal for choosing leftward. So there you have a 0% motion case, and the monkey is going to pick. So that's just a reason to think that this is as good a paradigm of a free choice as at least a burdens asked paradigm is. We'll go back again to that 0% motion toward the end. So the second version of this objection is that the random dot motion is a categorization task, not a decision task. So basically, the monkey's not deciding which way to move his eyes or deciding which way the dots are going. He's just trying to classify the stimulus into one or the other directions. This is a type of rightward motion stimulus, or this is a leftward motion stimulus. And there I'm going to say, okay, that's right, but actually what categorization is a sort of kind of decision. And one reason that we think that this is true is that there are other studies of categorization, particularly in this very same area, and the neurons show very similar kinds of dynamics. But I also think that just abstractly speaking or philosophically speaking, categorization is just a degenerate kind of decision, typically a decision where the boundaries are fairly clear-cut. And so what decision making is just a more elaborated version of a categorization task. And interestingly, we have now, people have done work that shows that LIP can, the neurons in LIP reflect categorization decisions on a variety of different rules. So you can have the very same stimuli categorized according to one rule and then another rule that differs, so the categorizations would be different. And so it's clear that LIP neurons are actually doing this or being modulated in their dynamics by some higher order areas that are telling them what's the rule in place, and their dynamics are actually following that. And so if you think decision making is something that requires some kind of executive activity or higher order decision making or higher order control in order for it to be decision making, LIP neurons seem to be doing exactly that kind of thing. A third objection that this is the wrong task is that what this random dot motion stimulus does is it's an example of a decision that, so a decision that the dots are moving to the right, or a decision that the dots are moving to the left. But if you're interested in human decision making, what you're interested in is more decisions to, like, what do I do now? I have the gun in my hand. Do I decide to pull the trigger or not to pull the trigger, etc.? So especially if you're interested in moral responsibility, you're interested in decisions too. But I think that, first of all, there's good evidence for thinking that what LIP is really doing is governing decisions in particular decisions to move one's eyes one way or another. But secondly, I think that those two kinds of decisions that and decisions to, are sort of interchangeably framed. So a decision to do X is just a conditional decision that. So if if conditions are such and such, then do X, right? So if a decision that Y, then do X. So again, I don't think that the fact that this could be classified as a decision that kind of task means that it's not the kind of decision to do something. Okay, so those are the objections. I think that this is the wrong task. But you might think this task, maybe this is telling us how humans do this particular perceptual task, but we're not really interested in that kind of task when we're thinking about human decision making. We're thinking about like decisions to get married or what college to go to or things that are not given to us in terms of perceptual content. So the decisions that we care about are essentially decisions that are over propositional contents. And what I would submit is that this kind of framework is just really generic, and the bounds that are identified can be identified as propositions. So in this case, what the monkey is deciding is deciding to or that the dots are moving to the right or that the dots are moving to the left. But those hypotheses could be anything else. It could be to attend UC Merced as opposed to attend UC Berkeley. And it's just that the neurons representing those propositions would be different populations of neurons. So the model itself is purely general. And certainly one difference between monkeys and us is we can represent, I think, more complicated propositions than monkeys can represent. But there's no reason to think, we know for sure that there are neurons that can represent the propositions we can represent because something in our brain has to do that. So there's no reason that we can't use this kind of framework to model that kind of decision making. So just think of it, instead of those H1 and H2, just think of two different propositions and the same thing holds. Another thing that might make you think this is not the kind of decision that we're interested in is that the random dot motion is a binary task. So the monkey has to either decide to move his eyes to the right or move his eyes to the left, but we have decisions that, where are we going to go for dinner tonight? Well, there are like 20 different things that we could choose. But Shadlin's lab has done a bunch of experiments and shown that this very same model can be expanded to as many dimensions as you want. And so what you get is that different kinds of baselines might apply the more decisions that you have, but in a sense, the model is just completely scalable to as many decisions as you want. And then I think the biggest objection is that when we make decisions about things that matter, we're actually worried about things like value. And this random dot motion doesn't seem to incorporate value. But that's actually just an artifact of the task itself, and you can easily make these neurons reflect differences in value. So here's an example of the difference in firing rate in these very same neurons when you increase the reward size. So as the reward gets bigger, the neural activity in the LIP neurons gets bigger. So if you associate direction of motion to the right with like a raisin instead of a drop of juice, you're going to get an effective increase in the LIP neuron firing if the monkey prefers raisins to juice. And similarly, you can also affect the activity in those neurons by changing the probability or the expectation that the monkey has that something or other is going to lead to reward. So both value and probability or expectation is multiplexed into these neural signals. And so pretty much any kind of contentful variable that you think of when you think about decision theory can be accounted for with this kind of model. So these neurons can do content, they can do value, they can do probability. So all of decision theory essentially is something that can be incorporated into the model of these LIP neurons. All right, so the last objection is that this is just the wrong kind of model because monkeys are just so different from humans that it's kind of inapplicable or silly to try to draw lessons from studying monkeys to humans. So I think the biggest, at least to me, the most worrisome question that you might have or reason to think that this is a wrong model is the fact that we have language and monkeys don't. And so I think a big and kind of unknown question that we might have is whether language is necessary for decision making. And I'll give you a bunch of prima facie reasons for thinking that it's not necessary to decision making, but I may not be able to convince you, and I still have some doubts about this. So at least we can narrow down what the kind of worry is. So one thing to point out is that when I say we have language and monkeys don't, I don't mean to imply that monkeys can't represent propositions. So I think monkeys can represent propositions. Linguistic capacity does not necessarily track propositional capacity. So I think that, as long as you think that propositions can be represented by neural populations, there's no reason to think that monkeys can't represent propositions as well. A second thing is that even though monkeys don't have language, this could be a very general model for decision making, and it's just that the kinds of substrates over which the decisions are being made could be different. So the model could hold, but it may only explain perceptual or other non-linguistic decisions in monkeys, but also extend linguistic decisions in humans. Another thing to recognize is that when we say monkeys don't have language, we don't mean that monkeys don't have symbolic capacities. So there's plenty of evidence that monkeys can use symbols in order to perform tasks. So they can represent symbols as quantities that can play a role in decision making, just not language itself. And then the real question, I think, though, is language central to decision making. So you might think that when we make decisions, what we're operating on are these linguistic contents. But there's some work in psychology that suggests that this might not be the case. This might be sort of a user illusion in a sense that we have. So there's quite a bit of evidence now that a lot of decision making proceeds sort of subconsciously and maybe not linguistically. So there's work that shows people make better decisions when they're not explicitly thinking about those decisions. How far you want to extend that, I think that could be debated. But you might think that decision making is a much more primitive capacity than language use, and that all kinds of systems have to evolve effective decision making capacities, and that humans then sort of co-opted these and learned to couch things linguistically, but that the real work going on, the more primitive and basic work, is going on at a sublinguistic level. So I think there are a lot of reasons to think that the fact that monkeys are language users and monkeys are not language users and we are, isn't reason to discard the notion that you can understand decision making in humans from looking at monkeys. All that said, though, there's nothing to rule out the possibility that some kind of linguistic representation might be essential to the kind of decision making that we're interested in when we think about human decision making, and more specifically things like moral responsibility. So if that's the case, then I think it's an interesting question to consider what linguistic capacities might do for us. So what do we get, or what abilities do we have in virtue of our language capacity that monkeys don't have? So one thing that I think is clear is that language permits us to represent more things than the monkeys can represent. So even if decision is conserved, it may be that we can just do more complex decisions or use our decision-making mechanisms to process more complex contents than monkeys can do. So that's, I think, undoubtedly true. The more interesting thing is whether what language allows us to do is make abstract decisions. So it may be that the contents that the monkeys can operate on are going to be very stimulus bound or perceptually bound or modality specific, and that, you know, if you ask the monkey to decide, let's say, so this we know, if you ask the monkey to decide, are the dots moving to the right or left, and to indicate that decision by moving their eyes, you get activity in some LIP cells. And if you ask them to indicate the dot motion by moving a lever, you don't get activity in LIP, you get activity of a very similar sort in a different part of the brain. So in that case, you might think, well, those monkeys aren't representing the direction of motion per se, they're representing the motion as tied to a particular response. And you might think we can do that, but we can represent more abstractly that the motion is to the right or the left, totally independently of any kind of response. So it's possible that what language allows us to do is to abstract away from these kind of stimulus and response bound kinds of pathways and have some kind of general abstract representation. But that could still be true, and this could still remain a good model for decision making. And that said, it's also possible that we just haven't found the nature of an abstract representation in the monkey, in part because we haven't figured out what we need to look for. So I think those are open questions and very interesting questions that neuroscience and cognitive science needs to pursue. But I think that the fact that monkeys have no language and we have language only gives us some reason to doubt how far we can push the analogy between monkeys and humans. Another, and not very good objection, I think, to using monkeys as a model for decision making is the claim that monkeys aren't conscious. Now, at some basic level, I think this is just plain false. So I just think it's not plausible to think that monkeys are not conscious at all. But it may be more interesting to think about whether they're self-conscious in an important way that's relevant to decision making. So it may be that they're not conscious of the contents of their thought in the way that we are aware not only of what's out there that we're representing, but the fact that we are representing those things. It's not, I think, plausible that they're unaware of the representations themselves, but unaware of these metacognitive states, the fact that they are representing, the awareness of the fact that they're representing things. And it may be that one of the important ingredients in what we think of when we think of human decision making is, in fact, this metacognitive ability, the ability to reflect on our own cognition. And I think you might think it's plausible that monkeys don't have that ability. However, Mike Shadlin has developed a task to assess this, and I think there's pretty good evidence that monkeys do actually have this kind of metacognitive ability. So in this post-decision wagering task, the monkeys so there are two versions of the task. Basically, the monkey's given the same kind of task where he has to decide to what direction the dots are moving, but in some versions of the task, he gets just the regular stimulus, the target comes up, and then the monkey gets a signal that he's allowed to move his eyes. So there's a fixation point that goes off, and then he'll report the decision that he made by moving his eyes to the right from right to left, to the right or to the left. So that's this lower trace here. But in some versions of the task or some trials, the monkey is given a third option, and that option is essentially a surefire reward, but a much smaller reward than he would get if he's right. So think about it. If the monkey knows that he's right, he wants to get the full reward. So he'll pick the direction that he knows that the dots are moving. But if he thinks that he might be wrong, he might think, well, it's better to get some reward than no reward. So in the cases where he's not sure about his choice, he can actually opt out and choose this surefire reward. So that's what happens in that top task. So you might think that happens when the monkey doesn't have a strong enough signal. And in fact, that's what you see. You see that in the cases where the monkey isn't given, so in the cases where the monkey actually chooses that opt-out option, the neural activity is somewhere between what it is in the normal cases. And more importantly, when you look at the cases in which he does opt out when he has the ability to opt out and he doesn't opt out, you see that he actually gets better at the task. So the monkey is, the choice to opt out increases when the monkey's decision is harder. And similarly, when he does opt out, and you look at the choices where he doesn't opt out, he performs better than when he doesn't have that option to opt out. Okay, so all of that suggests that the monkey is actually choosing here and not picking. He's not just making random decisions, but he's also deciding what his evidence is, what's the quality of his evidence, or what reason does he have to pick one thing or the other. And if what we're looking at is actually a measure of confidence, it suggests that the monkey actually has kinds of metacognitive states where he can assess how good his evidence is or how sure he is in his decision in order to decide whether or not he wants to opt out. So I think this is a really interesting study. It has a couple implications. One is that at least it's prima facie evidence that the monkey is self-aware. And it might give you some reason to think that monkeys are more conscious than many people have given them credit for being. So you might think it's some sort of inflationism about monkey consciousness, and it brings monkeys and humans closer together with respect to this kind of decision. Or there's a deflationary interpretation as well, and that is that there are some representations of consciousness that actually succeed in driving action, but you might think that doesn't amount to some kind of subjective awareness or accessibility to consciousness. In that case, we're talking about evidence that's not really evidence for metacognitive states, or now we're getting into real philosophical territory. If you're a higher order thought theorist of consciousness, you might think that those higher order thought theories are disproven by this, that here's an example of a metacognitive state that is not sufficient for awareness, right? So you have a higher order state, yet no consciousness in this interpretation. So this would lead you to a general deflationism about consciousness measures and metacognition in general. So there are two ways we could interpret this data. And one thing that would be nice in order to decide whether we should go for the more inflationary or the deflationary interpretation would be to understand how this maps onto human experience. And so I had tried to do a study where we basically do the same, we replicate this post-decision wagering task with humans, the one that the monkeys did, and unfortunately, the postdoc that was working on it never got to do the experiment. So this is an experiment waiting to be done. If anybody has access to an eye tracker and wants to do this experiment, I suggest you go for it. But the idea is basically see whether human explicit confidence measures where we know that there's metacognition going on gives you the same kind of dynamics. It's still going to be some kind of indirect evidence, but it'll be closer evidence about whether the metacognitive states are what we're seeing in the monkey data or not. All right. The last objection to this wrong model, or last version of the wrong model objection, is that monkeys, even though they may have some kind of metacognitive states, they're not self-conscious in the required way for it to be relevant to decision making. Now, I think the first problem with this suggestion is it's not at all clear why self-consciousness is necessary for decision making. At least decision making, very simply speaking. But if you're worried about decision making, moral responsibility, and freedom, you might think there might be some requirement for self-consciousness. So you might think that the capacity for freedom requires some kind of conceptual background for which, let's say, the question of am I free must arise. If you think you must be able to ask am I free, you must have some kind of level of self-consciousness. So Galen Strachan has suggested that freedom can only be ascribed to creatures for whom the question of freedom can arise. Or it might be that you need some kind of concept of yourself in order to be a free agent. Now, it's not clear to me that those considerations, even if they're valid, really necessarily apply to freedom. It may be more applicable to questions of moral responsibility. That is, you might have to really be able to self-reflect in order to be held morally responsible. And you might think that freedom itself may be a lesser condition. But just to throw out something tantalizing, is there have been recent studies that suggest that this ability to be self-aware is actually much more widespread than people had originally thought. So people had found evidence that apes were self-conscious, but they hadn't found it in other creatures. But now there's evidence from macaques and some other animal species that they in fact are self-aware, at least given sort of the standard kinds of tasks. And then the last objection that this is the wrong model is just that monkeys are not free. And in a sense, I mean, yes, in a sense, these are not free, but in the type of freedom that we're worried about, I think that's begging the question, right? We have to first decide what freedom is before we can claim that monkeys are definitively not free. Okay, so in this last part of the talk, I'm going to turn to the question of free will and just ask to what extent this kind of work could inform us. So go back to Bird and Zass and this problem of 0% motion. So what can we learn from doing this 0% motion task? So one thing that's really interesting about this task is that you can replay the very same digital video over and over again. So it's not just the case that the two motion strengths are matched, that there's 0% motion signal, but you can show the same stimulus over and over, so there's not even variability in the motion signal. Now, is this relevant to discussions of free will? Well, there are certainly some people who think so. So Michael Hauskeller says, to find out whether you're really free, you'd have to be in a situation where no reason is stronger than any other, a situation like the one in which Burden's unfortunate ass finds himself. If you're able to make a decision in such a balanced situation, you'd thereby demonstrate the freedom of your will. So that, I think, is a very naive view of what freedom of the will requires, but the 0% motion task is a perfect task for determining whether that's true. So here we are in our 0% motion. Monkeys, of course, don't know whether or not the motion is 0%. Here's another example of one of your, at least not so far-flung colleagues in California. The question of whether libertarianism is true just reduces to the question of whether some of our torn decisions, those are decisions where we seem equally pushed in one way or the other, or pulled in one way or the other, are undetermined at the moment of choice. This, of course, is a straightforward empirical question about the neural events that are our torn decisions. So if it's a straightforward empirical question, you'd think that being able to stick an electrode in a monkey brain and give them the 0% motion task is a straightforward empirical way to find something out. Then what I'm going to argue is that it's not. So first of all, you give the monkey this 0% motion task. If the old style Bird and Zass thought was true, the monkey wouldn't be able to just decide. He would just keep staring at the 0% motion thing because there's no reason for him to pick one way or the other. But we find that, in fact, the monkey makes a decision. Okay, so even without having anything in the stimulus driving him, he is deciding something. Moreover, what we find is that the monkey makes about 50% of the choices to the right and 50% of the choices to the left. So even though he's getting the very same stimulus over and over again, he's not doing the same thing. It's not like he's an automaton just replaying the very same thing over and over again. So you get these variable answers. So you might think, well, that proves that the monkey's free. He's got the very same stimulus, yet he's doing two different things. That's an exercise of free will. We're done. Monkey's free. However, it's not that simple. So back to your original question, turns out if you actually sum up all the choices, all the times that the monkey has chosen rightward motion with 0%, and you sum up all the neural activity from that choice over multiple trials, and then you do the same for the leftward motion, you see there's a slight bias in activity underlying those kinds of choices. So then you might think, well, the monkey's not free. The neural activity is driving his choice. But then you could look at individual neurons and say, oh, but for each individual neuron, there's stochastic activity, so those neurons are undetermined, or there's an indeterministic signal in there. So if you're a libertarian, that suggests that the monkey's indeed free. But then, if you look back, if you look lower down, if you, let's say, take a look at the synaptic boutons at any given point, you find out that there's differences in the microstructure of the neurons in cases where the stochastic activity, or where the activity seems stochastic. So at a lower level, it looks like it's determined by microfeatures. And my ultimate argument is that there's no place at which you're going to be able to stop and tell for certain that here's a place where indeterminism is at work and the monkey is, in some libertarian sense, acting freely, or us for that matter. Basically, there are two different problems that I think neuroscience is not going to be able to solve. So one of them I call the problem of fundamental neural indeterminacy, and that is that we can't tell whether these apparently deterministic or indeterministic behaviors is what I would call really metaphysically deterministic or indeterministic, right? So that what looks at one level of analysis to be indeterminism, if you look finer grained, you'll see that there are physical underlying forces that are different in those cases that might explain what seem to be different behavior at a more macro level. But you can keep doing that all the way down to the level of fundamental physics. So if there's any science that's going to answer this question, it's going to be physics. And then it's not clear to me that the answer is going to really give us any more information about what's going on at a relevant neural kind of level. The second problem is even harder, I think, and that's the problem I call of exhaustive neural determination. So this is just probably 1980s-ish sketch of the visual system of the monkey, only the visual system of the monkey, different areas and their interconnections. And we're talking about areas of the brain each has millions of neurons in it. And you can see it's a pretty complicated interconnected web of areas. So when you see differences that look stochastic by recording at one part of the brain, you can't tell whether the signal that looks stochastic is coming from that part of the brain or is just the effect of influences from other parts of the brain that you're not measuring at that time. So to actually determine whether things are stochastic or not stochastic, you'd have to be able to measure everything from everywhere at the same time and also know all of their interconnections. And to just illustrate how hard this is, here is a diagram of C. elegans. It's the only, at least last time I checked, the only organism for which we know all the neurons and all the interconnections. There are 302 neurons, and that's what the web of interconnections looks like. So now think about a system with billions of neurons in it, and think about how highly, if each of those neurons has 10,000 connections, this web is just going to be completely intractable. So there's no way that we're going to be able to isolate subsystems or know everything about all the neurons at the same time. So we're never going to have the kind of information that we need to untangle this question about indeterminism versus determinism. So all of those, there are enough of them, publications in neuroscience that say, we found free will or there are no free will. None of those guys know what they're talking about, okay? These problems are intractable. So does that just say that neuroscience can't tell us anything interesting about these philosophical problems? I don't think so. So for one thing, I think, so it's not going to tell us whether determinism or indeterminism is true, but I think it's telling us something pretty interesting, which is that this obsession that philosophers have had about determinism or indeterminism and the question of freedom is really just kind of misplaced. It's not looking at things at the right kind of level. And I think that what we can learn from understanding the mechanisms is just helping us to flesh out reasonable models of what decision is. I think we have to recognize a couple things. That is that just the fact that we're finding some kind of mechanistic basis to, let's say, decision making doesn't automatically mean that there's no there or that we're not free, because what we're interested in really is mindedness and not mechanism, and those things aren't mutually exclusive. So it doesn't follow that if the brain is mechanistic, that therefore we don't really have intentions and we don't really think and we don't really make decisions. It's just that we've been thinking about this in the wrong kind of way. So if you're interested in free will, I think what you need to be thinking about are things like reasons responsiveness, which the monkey's a good example of. You give him more evidence, he's responsive to that kind of evidence. You give him more value, he's responsive to that kind of value. So you think about things like reasons responsiveness, intentionality, maybe metacognition, but those are the things that matter when you're thinking about freedom, not just question of, well, is there a bit of indeterminism somewhere in the system? So I think all of these things require more explanation, and I don't think that we're going to get any answer from neuroscience about human free will, but I do think that what we learn from neuroscience will help us constrain and enrich the kind of models that we can build. Okay, so just to summarize, I argued for this sort of generalized model of decision making that I think we can learn from monkeys and apply to humans. There are reasons to believe in it, including the fact that we have a strong evolutionary relationship with them. There are brain homologies. There's identical performance in these tasks, and that we can actually give an account of all the elements of decision theory that can be accounted for in this model. And I considered a bunch of objections. So I think that this task is analogous to a lot of tasks that philosophers have used to illustrate the question of free will. I think that the question of contents can be answered in the context of this kind of task, and that we can think of how to expand the notion of content to apply to humans and everything humans can do. I think that the biggest issues are capacity issues, like what is the role of language in decision making, and potentially what is the need for a role of metacognition, but I think we've made some inroads into understanding metacognition in animals. And I think there's a lot of outstanding questions both in philosophy and in neuroscience. So here are some philosophical / scientific questions that maybe some of you will address in your future careers. Does linguistic representation fundamentally change deliberation and decision-making mechanisms? And if it does, in virtue of what? In virtue of its content or in virtue of its format? Do monkeys have any of the same kind of metacognitive access to their decisions that humans do? Does freedom require some kind of self-conception or a role for awareness or consciousness? And are monkeys different in those kinds of ways, in a way that matters for the philosophical question of free will? And then I haven't spoken very much about this, but I think there are more purely neuroscientific questions that we could ask. So when I mentioned that all decisions occur at a certain threshold, there are big questions about what sets that threshold and whether that threshold can be altered. So those kinds of mechanistic questions are really interesting. What is it that sets the value or titrates the value representations? And how can we conceive of abstract decisions? So is there some way of linking decisions only to output modality in monkeys, or is there more abstract representations? And how, if there are abstract representations in humans, how are those represented? Of course, if monkeys don't have them and we do, we won't be able to answer that question purely from recording from monkeys. But there are some kinds of studies that we can do on humans. And then a more general question of how high-level or executive function interacts with the low-level processes that people have been able to investigate and that I've talked about here. So I think there's lots of room, both philosophically and neuroscientifically, for inroads to be made in understanding decision-making and for understanding better what the nature is of free will. So thank you very much for your attention.